Hi, everyone. Really great to see familiar and unfamiliar faces. Welcome to Encrypt. I'm David. I'm from D-Wallet Labs. And before we start, I want to say thank you to our co-hosts and sponsors, the MPC Foundation, Silence Laboratories, GSR, and Lightshift. Yeah, I won't take too much of our time. I want to kick off what I think will be a really, really interesting, heavily focused on research conference. And for our keynote, I am very happy to welcome Zvika Brakerski. Zvika is a professor at Weizmann Institute of Technology. Science, sorry. And he's also an advisor at D-Wallet Labs, and he'll talk about the history of FHE. And yeah, thank you, Zvika.
Hey. So I think I turned the mic on. Can you hear me? Excellent, good. And this is my clicker. Can you see this? No, you cannot, right? OK, so there's no pointer, I think. Never mind, I'll manage. So hi, everyone. Yeah, so I'm Zvika, and so I'm going to talk about fully homomorphic encryption, or FHE. It's doing pretty well recently, which is a great thing. And I'm going to talk about how we got to this point and a little bit about where we go from here. So you may or may not know what fully homomorphic encryption is, but I certainly did not know until December of 2008. I was a first-year PhD student, and I went to my first cryptography event. So this was a workshop, cryptography workshop at Tagstuhl in Germany. And I actually, dug up from my email the preliminary schedule that they sent for this event. And on Wednesday, so it was a week-long workshop, and on Wednesday there was supposed to have been a talk by Craig Gentry. So Craig was recently graduated PhD student from Stanford. I did not know him at the time, but there was no title for the talk. It was to be announced. And later on, when after the workshop already started, they sent an update, and the updated title was Fully Homomorphic Encryption, which to me, I didn't know what that was. But people seemed to be pretty excited, like all the big names. Oh, there's a talk about fully homomorphic encryption. We have to go. Anyway, you go to the talk. This is what you do. You go to the talk. So I went to the talk. And sort of Craig Gentry really sort of laid it on us. There was a lot of new techniques and new ideas. And afterwards, in the coffee break, people were sort of trying to figure out whether these things work and whether they fit together. And so it was obvious that this was sort of going to open very interesting research avenues. Yeah, after the talks, everybody went to get beer. So yeah, this is me. And just by accident, I ended up sitting next to Craig and got this, to me, cool frame, photo frame, where Craig and I are in the frame. And also there was my friend Vinod Vaikuntanathan, who was just graduating from his PhD from MIT. And he's also going to play a role in the story that I'm about to tell. So we were kicking off at a good start. So this is where I heard of fully homomorphic encryption. But to tell you what it is, we need to go even further back in time. So 30 years further back, so almost a half century ago, in 1978, Rivest, Edelman, and Dertouzos published a paper called On Databanks and Privacy Homomorphisms, where they presented this idea, this notion of fully homomorphic encryption. So we used to think about fully homomorphic encryption as something that's kind of new, but people thought about it back in 78. And the motivation then was this notion of using mainframe computers. So back then, you couldn't just, if you just had a company, you couldn't afford your own computer necessarily, and you'd rent computer cycles from these big companies that had these mainframe machines. So you just have a dumb terminal that would be connected to this big mainframe computer. And then if you did your, I don't know, accounting or whatever of your company, you would do it on this third-party machine. And this raised privacy concerns because this was potentially sensitive information of your company, and it was being processed by a third party. So, I mean, the obvious idea was to encrypt it. But if you send encrypted information, if you encrypt the information, then send it to the mainframe computer, then how's it going to compute on it? So the cool idea of Rivest, Edelman, and Dertouzos was that this is actually not contradictory, that you can have both. So they proposed this idea of a fully homomorphic encryption scheme. And that's an encryption scheme that just has ordinary security. And it's a little bit funny that I'm saying it because back in the 70s, they didn't really know how to define security for encryption schemes in the way that we do today. The definitions that we use today only came up in the 80s. But it was, luckily enough, that was good enough. So they were saying, look, just whatever you want to require for your encryption scheme, you require it from this fully homomorphic encryption. But in addition, you want this additional property that if you have some encrypted input to some computation, so you have these M1 up to MK, so these are just, let's say, numbers that you want to compute on, and you have a function f that you want to actually compute on this information, then you can transform the encrypted input into an encrypted output without decrypting it all, so without violating the security of the encryption. So someone can actually perform this sort of translation from encrypted input to encrypted output without actually looking at the data. And they realized that this does not contradict the security of the encryption. So if you do this, then you can send your encrypted data to the mainframe computer. They would compute on it, send back the encrypted output, and then you'll decrypt it on your terminal and get the output. So this was sort of their idea of a solution. So they had this definition, but they couldn't achieve it. And it turns out it was a hard problem to construct fully homomorphic encryption. It was unsolved for a long time. Some people speculated that maybe it was even impossible to achieve. But then Gentry came and showed us that there is a way to do it. And Gentry's original solution, it has like a few different parts. The basic idea is to use these things called ID lattices. So actually it turns out that it really depends on what kind of operations you want to perform. So if your function, if you just want to add two encrypted values, then people actually know how to do that. But if you want to both be able to add values and multiply, then things become hard. And if you can add and multiply, then you can actually do anything. So I'm just going to focus on multiplication, and we'll just remember at the back of our minds that addition is something that you can do. So how do you create an encryption scheme where you can multiply values? So Gentry had these ID lattices, they kind of look like polynomials. So you embed your message into a polynomial, and polynomials are things that you can add and multiply in a meaningful way. But you had to find like an ID lattice that is going to have good structure that can be used for this type of construction. And that was an exhaustive computational process. You had to sample multiple times from this distribution and hope that you're going to get a good ID lattice that you can use as a secret key and public key for your scheme. So the key generation was like a very exhaustive process. In addition, these ciphertexts for this scheme had this property that's going to sort of stay with us for the entire development of fully homomorphic encryption. There's a noise component in the ciphertext. So this noise is just something that keeps growing as you perform homomorphic operations. And if the noise grows too much beyond like the noise capacity of your scheme, then the ciphertext becomes useless. So Gentry offered a way to do addition and multiplication, but you can only do it so many times before the ciphertext becomes useless. So you can do a few operations, but not everything. And so this was the first component, like a basic scheme. And then he introduced a second component, which is called bootstrapping. So if you read a little bit about fully homomorphic encryption, you probably heard the word bootstrapping. And bootstrapping is a technique for noise reduction. It requires additional computational assumptions, but that's not the point. The thing is that in order for bootstrapping to work, you need you actually need the basic scheme to have like a sufficiently simple decryption. So the ability to perform bootstrapping actually depends on the complexity of the decryption of the original scheme. So this is like a game of trying to come up with a basic scheme that has simple enough decryption so that you can bootstrap it. And actually, in Gentry's original idea, it didn't work. So Gentry tells this story that he started telling people that he had a fully homomorphic encryption scheme. And then he sort of did the calculations more precisely and figured out that there's like a little gap still between like what he can achieve in the basic scheme and what you need for bootstrapping. But he was already committed because he told people that he knew how to solve it. So he had to think like really hard what to do. And he came up with an additional trick called squashing that sort of made these things sort of closer together so that you can use both of them. Luckily, we realized with time how to get rid of it. So I'm not going to get into it too much. So this was sort of Gentry's sort of breakthrough scheme, and following that, there were other schemes that sort of used a similar blueprint. But with time, Vinod Vaidyanathan and myself sort of realized how you can simplify things quite greatly. And instead of working with these ID lattices, to work with sort of more standard cryptographic problems, in particular something known as learning with errors, or LWE. And there's a variant called ring learning with errors, or ring LWE. And these are sort of standard types of problems that are, at that point were used in cryptography. Let me tell you a little bit how to use them in order to simplify fully homomorphic encryption. So this is going to be a little bit of a technical slide, but I'm hoping to sort of introduce some of the terminology that you're going to encounter if you read about fully homomorphic encryption. So hopefully it's going to be worthwhile. So the first thing that we did was to construct this scheme that was based on ring LWE, and we used this method called tensoring. So what we did was to apply these sort of very useful scientific techniques One of them is called wishful thinking, and the other one is called like squinting really hard. So you combine these. So what do we do? So we were sort of hoping to be able to get a ciphertext that looks like a multiplication of two things. And what we did was to look at the decryption. What happens when you take like an ordinary encryption scheme, not homomorphic, that is based on, let's say, ring LWE, and just look at the structure of these things. And what happens when you decrypt a scheme like that is that you take the ciphertext, and you take your secret key, and you multiply them together. And this more or less gives you the message. More or less because there's this noise that I was talking about, but let's squint and put that on the side, okay? So it's a product of two things. And these two things, the ciphertext and the secret key, are both vectors. So multiplying them means to apply like an inner product. But again, whatever, like, it's just a product to us. And now what we want, again, is to figure out a way to look at a product of two messages and try to write them as a multiplication of something that depends on ciphertext times something that depends on secret key. And hopefully, if you can write it in this way, then you will get like a ciphertext that encrypts the product of two messages. So we have this equation from above that sort of m approximately equals c times s. And now if we have two ciphertexts, c1 and c2, that encrypt two messages, m1 and m2, then we can just sort of plug in the equations. And we get that m1 times m2 is more or less c1 times s times c2 times s. And now, as I said, I want to sort of put all the things that depend on c on one side and all the things that depends on s on the other side. And again, we're going to squint and pretend that we don't have vectors. But if we just had like numbers, c1 times s times c2 times s, then this is actually equal to c1 times c2 times s squared, right? So we can just sort of reorganize. And turns out that you can do the same thing with vectors. Instead of the ordinary product, you get like a tensor product or outer product, whatever. So like a big name. But you can sort of put all the C things on one end and all the S things on the other end. And then you get this, like the C1 tensor C2, in some sense looks like an ugly version of an encryption of M1 times M2. So this is sort of in the direction of what we want. We get something that we can compute just given C1 and C2. We get the two ciphertexts, and we get something that corresponds to the product. And when you decrypt it, you do something with the key, and you can decrypt it. So this is sort of what we want. But this is like an ugly ciphertext in the sense that this tensor product actually blows up the dimension of the vector. So if you started with a vector of dimension 1,000, then you're going to end up with a vector of dimension 1,000,000. So that's not so good. But back then, we were thinking about ring LWE. And ring LWE, you start with vectors that have a pretty low dimension. So you can still do a few operations like this before things get stuck. So this was sort of our original idea. And it already sort of makes a big difference in making the key generation really trivial. Because I told you that the encryption is just going to be identical to the encryption of a non-homomorphic scheme. So you don't have to sort of work hard to generate keys and to sort of come up with the right ideal addresses and so forth. You can just sort of use the structure that is already sort of known. And this sort of removed a big hurdle from Gentry's original scheme. But we still didn't like this sort of ugly ciphertext, and we tried to make it better. And what we noticed that if you take, so we want to take like an ugly ciphertext that looks like a tensor of two things, and convert it into a ciphertext that's just like sort of single vector, that just looks like something that you need to multiply with a secret key. And it turns out that you can do it. That if you take a ciphertext that is decryptable using s squared, and you have on the side some side information that is just the encryption of s squared under your original key s. So I can give you this, because this is just like, this is something that depends on the key, but it's encrypted. So at least intuitively, it should be OK to give this to the evaluator, to the person who's not supposed to know what's inside. And this would allow you to actually convert ciphertext with respect to s squared into ciphertext with respect to s. So this is a technique sort of known as key switching. And again, this is something that you're going to see in the literature now. And this was supposed to take ugly ciphertext and make them into nice-looking ciphertext. It didn't work just as I described it. You need a little bit to tweak with it a little bit. Let me not get into more details. But this is sort of more or less the idea. And this means that now the sort of like the syntax of the ciphertext looks OK. But there's still going to be noise buildup. The noise buildup here is going to be very similar to what happens in Gentry's original scheme. So we had like a similar problem of sort of taking the basic scheme and the bootstrapping and make them sort of work together. The second thing that we noticed here is that if you take, so remember, the problem with bootstrapping is the complexity of decryption. We want to make decryption easier. And what we noticed is that if you take like a ciphertext of this basic scheme and you try to decrypt it, actually you don't need all the bits. You can actually sort of remove a lot of the bits of the ciphertext and still get something that can be decrypted. And this is now called module switching. And just because you removed a lot of the bits, you also simplified the decryption process. And this actually allowed you to put the basic scheme and the bootstrapping together without needing squashing. And that was sort of a big achievement, because now you can just rely on this learning with errors or ring learning with errors. You didn't need any additional assumptions, and you can get fully homomorphic encryption. So obviously, we were very happy. But stuff's getting real now, right? Because we're getting a scheme that's built on like a standard cryptographic assumption, and maybe people are actually going to want to use it. This is not like Gentry's previous thing that was kind of like a fantasy land. This is like a concrete thing. So people are continuing to think about like how to do things more efficiently. And then at some point, Gentry sort of very shortly after came to us and says, "Look, guys, essentially said to us, look, guys, you're doing this module switching all wrong." At least this is what I got. Like, this is what I would say to myself. You guys are doing module switching all wrong. So the way that we were doing this was that we performed a lot of homomorphic operations. We got like this big annoying ciphertext, and then we did module switching to make it like more compact. But actually, the right thing to do is after every operation to remove the bits that are unnecessary. So after every step, after every computational step, you remove the unnecessary bits and you keep going. And that actually makes like a huge difference in terms of the way the noise grows. So in this BGV type schemes, the noise is going to grow much more mildly than it did in like the previous BV schemes. So if you want, let me try to illustrate. So you have this black container, which is sort of the noise capacity, like the number of bits that you have for the message and the noise. So the message and the noise sort of live in the same space, and they're not supposed to take too many bits. If they take too many bits, then the ciphertext becomes undecryptable. So in the original scheme, the blue part sort of represents bits that are taken by the message, and the orange part is bits that are taken by the noise. And when you multiply two of these ciphertexts in the previous scheme, like the number of bits that you need for the message is the same, but the number of bits that you need for the noise actually doubles. So this is what happens in the BV scheme, whereas in the BGV scheme, if you start from the same inputs, what you're going to get is that the magnitude of the noise remains the same, but the noise capacity, you look at the size of the container, that actually shrinks. And you might think that it shouldn't make a difference because like here you have more noise and more space, and here you have like a smaller amount of noise and smaller amount of space. But turns out if you do it multiple times, it does make a difference. And this BGV actually helps you save a lot. In addition, in this BGV paper, we also introduced this technique called batching. So this is again something that you may hear about when you read when you look at FHE literature. So I told you that these ciphertexts for fully homomorphic encryption are pretty big. But what we realized is that you can actually embed more information into like one of these big ciphertexts. You can actually sort of encrypt more than one message at a time. So if you care about amortized performance, then this BGV scheme can actually give you much more throughput than sort of the previous schemes just by encrypting more things and doing things in parallel. So this was actually sort of bringing things into a regime where people could actually start to implement and maybe think, well, maybe for some applications you can actually do it. And there were a lot of papers that sort of focused on trying to optimize and make things actually realizable in this for this scheme. But I was kind of lying to you by saying that I said, well, you might think that I wasn't lying, but I was not in peace with what I said before, that actually there is a difference between like big noise and a lot of noise capacity versus small noise and smaller noise capacity. It doesn't make sense. It didn't make sense to me. It works. Of course, this is correct, but somehow if there's justice in the world, right, then there should be a scheme where it doesn't matter, where like the absolute value of the noise and noise capacity shouldn't matter. Only the ratio should matter. So I was trying to think about it, and turns out there is a way to do it. Essentially, you need to reorganize things. You store your message sort of on the most significant bit of your container, of your noise capacity, and the noise goes in the least significant bit. And then if you do things right, when you do the multiplication, like the noise grows, but it grows sort of outside of the container. So you get performance that is similar to what you get in BGV, but without the need to do the module switching. So you stay with the same modules throughout. And So this scheme was based on learning with errors, and then there was an adaptation by Fan and Vercateran based on ring LWE with a lot of useful optimizations. And this is also sometimes implemented. Now it's called BFV sometimes. So this is, again, another sort of way to try to do homomorphic encryption in a way that is sort of actually usable, practical. I don't know. Yeah, so this is sort of some steps that were taken along the way. The next thing that I want to mention is the scheme by Gentry, Sahai, and Waters. This is like called approximate eigenvalue method. This is what I call it, at least. And they were suggesting something pretty interesting. So I told you before that for LWE and ring LWE, your ciphertext is a vector. And they were saying, let's just use a matrix instead of a vector. So this matrix does not help you to store more information. So you're still using the same amount of information, but you're just using bigger ciphertext. So instead of a vector, it's going to be instead of thinking about your ciphertext as one LWE encryption, you think about it as a bunch of those things, and they form a matrix. And then you can do homomorphic evaluation using sort of matrix multiplication, some version of matrix multiplication. And yeah, so in some sense, if you want to think about these diagrams, in the GSW scheme, somehow the information about the message is sort of spread throughout because you have a lot of these vectors. So in each one of these vectors, your message is represented slightly differently. So in some sense, the information about the message is smudged throughout this sort of noise regime, and your noise is still sort of stuck in the beginning. So at least, hopefully, it gives you maybe some vague picture of sort of how things behave in the scheme. And it's not immediately clear what it's good for. So in the original paper, they tried to rationalize some things, but it was like a new idea, and it was very interesting. And it turns out that even practically, it had very interesting consequences. So it turns out that if you think about bootstrapping as done in this GSW manner, then you can actually get very efficient implementations or even sort of practical-ish implementations of the bootstrapping technique if you add some additional optimizations on top of it. And this led the schemes like FHE and TFHE down the line, which sort of add a whole family of optimizations in order to make bootstrapping more efficient using the GSW method. So I think maybe a lot of people, maybe in this community, heard about TFHE, for example, but I think it's less known that this is sort of an optimized version of a GSW style scheme. So there's the whole family that lives there, and the TFHE people sort of really did a really great work in taking this sort of very theoretical thing and making it practical. I should say that for theory of cryptography, the GSW scheme is extremely important, both in terms of the asymptotic analysis for noise, for fully homomorphic encryption. If you care about a theory thing, what is the polynomial that describes the noise growth and so forth, then you can do things with this scheme that you could not do with previous schemes. And actually, you can use this actually started a line of works that created a framework for a large number of cryptographic objects that we don't know how to get in any other way. Things like attribute-based encryption, program obfuscation of sorts, traitor tracing schemes. So these things are still not at the practical regime, but who knows? Maybe in 10 years we're going to have a talk about that. So for theory, these things are extremely important. Another scheme that I want to mention is the FHE over the reals. So we're already at 2017, and the CKKS scheme noticed something that's, again, really cool and interesting. So we kept saying that we wanted to, let's say, add and multiply ciphertext and so on, but we always said that the output needs to be really the correct value. And they noticed that in many cases, if you think about sort of real-valued systems like machine learning algorithms and so on, the least significant bits of the output don't matter that much. So it's OK if the least significant bits are missing, or if they're dirty, or if it's not exactly what they're supposed to be. And then they devised a scheme. Again, I'm using my sort of schematic description here, where when you do a multiplication between two values, your sort of the least significant bits of your output actually sort of dip into the noise. So the noise is actually going to sort of interrupt with the least significant bit of the output. But if you're OK with that, then it gives you it allows you to perform functions that are sort of over the sort of real value. You can think about them as being over the real valued field. And again, this has direct applications like for machine learning algorithms, but also you can think about, so you want to do so I told you the bootstrapping depends on the complexity of the decryption. So now you can try to sort of characterize your decryption in terms of a real valued function, and this can also lead to efficiency gains. So that's another sort of great idea that now people are trying to use for various applications. So these were like a few ways to sort of implement this basic idea of a fully homomorphic encryption scheme that takes an encrypted input. There's a public key, there's a secret key. You encrypt with the public key, maybe you do some evaluation, and then you decrypt with a secret key. Now, people are trying to think, what happens if there's multiple users? So what happens in a setting where you have a bunch of users, each one has their own input, and you want, again, to privately compute some joint function of all of these inputs. And somehow, if you want to use standard homomorphic encryption, then everybody would have to agree on a public key and encrypt their data with respect to this public key. So you could try to do this. So this is one approach. But people were also thinking about this thing called multi-key fully homomorphic encryption. So this is sort of trying to do things in an even more decentralized way. So in multi-key fully homomorphic encryption, each party doesn't even need to know that the other parties exist. They just generate their own secret key and public key. And then they can use their individual public key to encrypt their input. So everybody can know the public keys, of course, like third parties can also encrypt with respect to my public key. But there's going to be a bunch of public keys that are living in the system, and everybody's allowed to encrypt with respect to the public key that they prefer. And you still want to be able to combine, to perform homomorphic evaluations on all of these different messages where each one is potentially encrypted under a different public key. So this is called multi-key fully homomorphic encryption. And turns out that you can do it. You pay, again, in sort of the asymptotic performance. So you take like a bunch of encryptions and a bunch of public keys, and you can do homomorphic evaluations. You can come up, homomorphic evaluation. You can come up with an encryption of like the function f on all of the inputs. But now, in order to be able to decrypt it, you need to have all of the secret keys that are associated with the parties whose public keys you used, right? Because it's like a function of encryptions, each one under a different public key. So if you want to decrypt the outcome, you need all of the secret keys. So what do? Either you run one of those secure multi-party computation protocols, and sort of each party with their own secret key in order to compute the decryption, or there's a method, it's called threshold multi-key FHE, where this can be done in certain schemes just using a single message. So every party uses their own secret key. They look at this like sort of big ciphertext that depends on everybody's public keys and secret key, apply some local operation with their secret key, send it out, and then there's a way to combine everything and get a decryption of the message that you wanted. So this is multi-key FHE. There's still some questions about even asymptotic efficiency of this type of primitive. So we have all these great ideas. I said efficiency improvements and so on. But now it's, someone needs to write the code, right? So we get to the point where people say, OK, like you convinced us, this is a good idea. Let's try to write the code and see how it performs. And here, sort of, if you do anything that has to do with programming or fully homomorphic encryption and so forth, then this guy should be your hero. So Shai Halevi did this really pioneering work from the get-go on implementing fully homomorphic encryption. Even from the days of sort of Gentry's original scheme, he had this code of implementation and some challenges for the key generation and so forth. And sort of he and others kept working to create HElib, which was the first software library for fully homomorphic encryption. And I think to date, this is sort of one of the most prominent software libraries in existence for this. And HElib is an implementation of the BGV scheme with a lot of optimization. So like obviously there's a lot of ideas that need to go in order to take this sort of very theoretical thing and make it into something that you actually can use. And there's a sequence of papers and a sequence of ideas, and also a lot of very insightful tricks that are not written in any paper that you need to look at the code in order to understand that go into this software library. So like really amazing work. And this sort of paved the way to many other software libraries. So there's a few examples here. Probably by now there are more that I'm not even aware of. Maybe you guys are writing your own thing under the hood, and we'll all know it in a while. But yeah, so people are actually implementing fully homomorphic encryption. That's great. So yeah, so here we are. This is now. This is Amir. This is you guys, right? So it's happening. It's happening. So fully homomorphic encryption is actually becoming a thing in the world. We have these workshops and online resources and libraries and compilers and hardware designs that's sort of targeted towards homomorphic encryption, and for-profit and non-for-profit and government organizations trying to sort of figure out how to implement and use these things, all these collaborations, even standardization efforts trying to come up with a standard for using fully homomorphic encryption. So there's really like sort of a burst of activity for a few years that sort of keeps growing, and that's really, really great. So thanks. And this brings up like sort of a bit of a sort of sign of caution. So we're trying to sort of argue that fully homomorphic encryption is a great thing. And we want to promote this idea and make people sort of realize that they can use it for various things. But we don't want to create misconceptions. Because FHE is so amazing, it's very easy for non-experts to be convinced that it's actually going to solve all of their privacy concerns without needing to do anything. So whatever, I have an application and it's not privacy preserving, so I'm just going to put patch homomorphic encryption on it, and it's going to become privacy preserving. And this is not the case. So while we want to make FHE more accessible, we should make the users aware of where it can and cannot be used. So again, many times you need to think before you apply fully homomorphic encryption, or I guess any cryptographic solution. But here it's sort of very easy to convince yourself of things that are not actually happening. So for example, right, we know that fully homomorphic encryption takes an encrypted input and allows you, again, without violating the privacy, you don't know anything, and you can still convert it into an encrypted output. But this only brings you to the point where you have an encrypted output. If you actually want to get the output and use it, then you actually need to use the secret key in order to decrypt. So someone needs to have the secret key. And with respect to this entity that holds the secret key, there's no privacy at all. So like this whole process that you did, I'm going to do it homomorphically and so forth, this is completely transparent to the party that has the secret key. So you need to think a little bit whether it's okay that you're actually not hiding anything from like an entity in your system. Another example, even if you did everything correctly and sort of managed to do the decryption the way that you wanted and you got the output, it's possible in some computations that the output itself actually contains private information that you don't want to reveal. And in this case, fully homomorphic encryption is not the right tool to use, right? Like if you're doing like running a big machine learning algorithm on a huge number of huge data set, and just like inside, and you derive a model from it or something. I hope I'm not saying like embarrassing words. You derive the model. If inside the model somewhere it is written like some private data of one of the users in your data set, then it doesn't matter at all that you did the whole thing privately. In the end, you're going to release the output, and that's going to violate your privacy. So you need to be careful. That's what I'm saying. It's not like the only tool for privacy, and it's not going to necessarily solve all of your privacy concerns. And yeah, there are even like sort of actual papers that show that in some cases, like if you're not careful, then you can actually get like security faults if you're misusing FHE. In particular, if you're doing things that depend on the key. Like whenever you use the key, you should be careful. Okay, good. So this is sort of where we are. We want to use homomorphic encryption properly. Let's try to take a short look into the future. What do we want? What do we want to achieve? So to begin with, I started by saying, we had all these great theory ideas, and we solved everything, and we all get prizes and drink cocktails, and everything is great. But are we really done? Are there other additional theory questions that need to be resolved? And there still are. So you shouldn't think that theory of fully homomorphic encryption is completely solved. Even if you only care about like this asymptotic notion where polynomial times equals efficient, and you don't really care about sort of concrete parameters, there are still questions that need to be solved, and there's even bounties. So Vinod has offered bounties to solve some of these questions. Essentially, there's really one family of methods that we know to construct fully homomorphic encryption. You have these noisy vectors, and you put them together in some ways, and the noise grows, and then you need to suppress the noise. And it would be good to sort of realize what we can do in order to break free from this paradigm. So these are theory questions. Of course, like if we're talking about implementation, so if we're happy with the state of things in theory and we want to sort of think about implementations, then of course there's also another set of challenges. So you can think about them as practical challenges, but there are also sort of theoretical questions underlying there. And you want to actually get concrete efficiency, right? Polynomial time is not good enough. We want to actually be able to run things. And the question is, what is the overhead of doing things homomorphically compared to doing them sort of in the plane, so without any encryption? So what we want is to compare the complexity of, let's say, doing a multiplication using homomorphic encryption to just taking like unencrypted values and multiplying them. And again, in theory, we can do like pretty well in theory terms. You can actually get a scheme that whose amortized overhead is only polylogarithmic in your security parameter, whatever that means. So somehow this looks really good if you're talking to a theorist, but the concrete performance is still sort of unsatisfactory. So we're still sort of struggling to bring down the overhead that we pay to perform operations homomorphically compared to just doing them sort of completely unencrypted, just saying, look, I trust you, just take my data, do the computation, give it to me back. So this is one big challenge. I should say that if we're just thinking about the communication overhead, so I was talking about like the amount of computation that you need in order to perform some operations, but you can also talk about the communication, like how many bits of encrypted data do I need to send you in order to send like a specific message. So you can think about the communication overhead for fully homomorphic encryption. And for that, again, sort of from the theory side, we had some pretty good solutions already from a few years ago, where you can get the overhead to be close to 1. So the number of bits that you need, the number of encrypted bits that you need to send is not much larger than the number of unencrypted bits. So again, that's good in theory, but this again only works if you're doing like a lot of amortization, so a lot of batching. You need to batch a lot of messages. And if you want to actually do homomorphic operations afterwards, you need to like unpack this batching. So this helps like to transport things from one point to the other, but we still don't have a good solution that also allows you to do the computation without blowing up the data too much. So there's the cost in computation, but also the cost in like the amount of storage that you need. And if you thought that was bad, the ciphertext or the data overhead of the ciphertext is big, but if you're looking at these keys, so I kind of glossed over the fact that you have a public key, and I said in the beginning, there's this additional side information, which is the encryption of S squared under S and so forth. So there's like a bunch of stuff, like a bunch of side information that you need in order to perform the homomorphic evaluation. We call this evaluation key at some point. And that's really huge. That's bigger than a ciphertext. And again, sort of the way that we were thinking about in the beginning, it's like, look, it's polynomial in the size of your security parameter, so you should be happy. It shouldn't be very big. But actually, so first of all, they're really big. Even just storing them, I think sometimes is a problem. But the bigger problem is not just storage, is that you actually need to compute on them all the time. Whenever you do a homomorphic evaluation, you need to actually access this evaluation key and sort of, I guess, bring it into your CPU, do stuff on it, and so forth. And as far as I understand, one of the big problems is even like the data bus that you have in and out of your processor is just can't handle the load of actually sort of swapping in and out these keys. So some people think about sort of trying to deal with it in hardware, or you can try to sort of improve, I guess the better solution is to just improve the way that we represent and use these keys. So that's like still a challenge in terms of the concrete efficiency of homomorphic encryption. So these are things that are sort of, I guess, actively being studied. Maybe also some people here are thinking about these problems. We can even think about going sort of beyond this. So I told you like a minute ago that I'm comparing how much it costs to do a multiplication homomorphically versus the amount of computation that you want in order to do a multiplication sort of in the clear. But what if you want to do operations that are not in this sort of, this implicitly assumes that you're using a circuit model. I told you that we know how to do addition and we know how to do a multiplication, which means that you need to break your computation into a sequence of addition and multiplication operations. So for example, if you want to do like a branch operation, they need to translate it into addition and multiplication. And that's pretty expensive. So let's think about like a very simple task. You have a database, like an encrypted database, and you also have an encrypted data chunk. So you want to insert value X into location I, and everything is encrypted. All the orange thing is encrypted. If you want to represent it as a circuit, your circuit is actually going to be as big as your entire database. So the way that we want to think about it, the way that I was describing things before, what you want is to compare the homomorphic evaluation of this thing into taking things in the clear, like into taking the plain data, and just running this huge circuit that's as big as the database. But that's probably not the right comparison, because that's not how like we actually do things sort of when we program things. So in general, sort of branching operations are like really expensive in homomorphic encryption. Yeah, it's actually lucky that we managed to do anything at all, right? These things are pretty important, and even though like FHE kind of sucks at them, we still managed to implement kind of a lot of things homomorphically. And sort of like a lot of algorithms that you would use sort of when you design a processor, for example, like pipelining, conditional execution, and so forth, you just cannot do if you have this encrypted data, because again, you're sort of restricted to this circuit model. And this was sort of one of my sort of favorite questions from the beginning. Like, this is a conceptual thing that you want to do differently. Like, what can you hope for? Can you get like fully homomorphic encryption that is comparable to the sort of random access memory complexity of your computation? So, for example, for this computation that's described here, you want to compare it against like a unit complexity, right? The amount of complexity that it takes to take an unencrypted database and an unencrypted data point and just inserting it into the database. That should be 1, right? So we want something that's going to be comparable in this model. And for many years, there's no like even direction on how to do it. But very, very recently, there's like this extremely interesting breakthrough by Lim, Mook, and Wicks. And they actually showed that using ring LWE, you could get fully homomorphic encryption in the random access model, random access memory model. So this is super interesting, so it's very new, and people are still trying to understand the properties of this solution. So for example, it has some oddities that we don't have in other homomorphic encryption schemes. Like for example, we know how to do it based on ring LWE, but not based on non-ring, on the sort of plain LWE assumption. And this is something that bugs us in terms of understanding, because for all other schemes, we have like ring LWE is used for efficiency, but you can also do things with plain LWE if you want. Here, this is not the case. And in terms of concrete efficiency, again, so people are saying, oh, it's completely impractical. There's like huge constants. It's very, very far from practicality. But we know that we shouldn't be deterred by these sort of things. So people just need to continue to think about it and see whether there's more that we can do in order to sort of use these techniques and sort of make better schemes, and maybe even sort of implement these ideas into the way that we do things. So yeah, so I guess the final question is are we there yet? So is it possible, are we already at the point where we can build like production level systems where FHE actually brings value? So we see in principle it's a great tool, but can we actually sort of get value out of it? Yeah, I don't know the answer yet. I guess that's for all of us to find out. So I'll just leave you at that. So thank you.